Einstein struggled to understand gravity on and off from 1907 onward. Finally, in 1912, he had a brilliant inspiration. Time, he realized, must be warped by the masses of heavy bodies, such as the Earth or a black hole, and that warping is responsible for gravity. He embodied this insight in what I like to call Einstein's law of time warps, a precise mathematical formula that I describe qualitatively this way. Everything likes to live where it will age the most slowly, and gravity pulls it there. The greater the slowing of time, the stronger gravity's pull. On Earth, where time is slowed by only a few microseconds per day, gravity's pull is modest. On the surface of a neutron star, where time is slowed by a few hours per day, gravity's pull is enormous. At the surface of a black hole, time is slowed to a halt, whence gravity's pull is so humongous that nothing can escape, not even light. This slowing of time near a black hole plays a major role in Interstellar. Cooper despairs of ever seeing his daughter Murph again, when his travel near Gargantua causes him to age only a few hours, while Murph, on Earth, is aging 8 decades. Human technology was too puny to test Einstein's law until nearly half a century after he formulated it. The first good test came in 1959 when Bob Pound and Glenn Rebka used a new technique called the Mossbauer effect to compare the rate of flow of time in the basement of a 73-foot tower at Harvard University with time in the tower's penthouse. Their experiment was exquisitely accurate, good enough to detect differences of 0.00000000000016 seconds, 1.6 trillionths of a second, in one day. Remarkably, they found a difference 130 times larger than this accuracy, and in excellent agreement with Einstein's law. Time flows more slowly in the basement than in the penthouse by 210 trillionths of a second each day. The accuracy improved in 1976, when Robert Visseau of Harvard flew an atomic clock on a NASA rocket to a 10,000-kilometer height, and used radio signals to compare its ticking rate with clocks on the ground. Visseau found that time on the ground flows more slowly than at a height of 10,000 kilometers by about 30 microseconds, 0.00003 seconds, in one day. And his measurement agreed with Einstein's law of time warps to within his experimental accuracy. That accuracy, the uncertainty in Visseau's measurement, was 7 parts in 100,000, 0.00007 of 30 microseconds in a day. The Global Positioning System, GPS, by which our smartphones can tell us where we are to 10 meters accuracy, relies on radio signals from a set of 27 satellites at a height of 20,000 kilometers. Typically, only 4 to 12 satellites can be seen at once from any location on Earth. Each radio signal from a viewable satellite tells the smartphone where the satellite is located and the time the signal was transmitted. The smartphone measures the signal's arrival time and compares it with its transmission time to learn how far the signal traveled, the distance between satellite and phone. Knowing the locations and distances to several satellites, the smartphone can triangulate to learn its own location. This scheme would fail if the signal transmission times were the true times measured on the satellite. Time at a 20,000-kilometer height flows more rapidly than on Earth by 40 microseconds each day, and the satellites must correct for this. They measure time with their own clocks, then slow that time down to the rate of time flow on Earth before transmitting it to our phones. Einstein was a genius, perhaps the greatest scientist ever. This is one of many examples where his insights about the laws of physics could not be tested in his own day. It required a half-century for technology to improve enough for a test with high precision, and another half-century until the phenomena he described became part of everyday life. Among other examples are the laser, nuclear energy, and quantum cryptography. The warping of space, the bulk and our brain. In 1912, Einstein realized that if time can